Hello everyone, I'm Harry from University of Edinburgh. In this occasion, I would like to present our work entitled Automated Planning for Configuration Changes. As you may already know that nowadays, the tasks of sysadmins for managing the computing infrastructure are becoming more and more complex than before. While cloud computing as an emerging IT service model gives more pressure for sysadmin. For example, a change in configuration must be implemented whenever there is a failure in the system in very limited time in order to satisfy the service level agreement. This is why configuration tool is essential to help the sysadmins to perform their task. Fortunately, there are many good configuration tools out there, and perhaps the most commonly used tools are using the declarative approach. These tools allows the user to declare the desired state of the system, and the tool itself will execute some actions to reach this state. This feature enables the automation of configuration tasks and makes the life of sysadmin easier. But unfortunately, there is a condition where we cannot use this feature at all. In this presentation, we will show the example case as well as how can we overcome this shortcoming. As outlined, first we will describe a little bit about declarative approach. Then we will present a simple example of configuration problem which shows the shortcoming of the declarative approach. And we will show you how our prototype can overcome this shortcoming. Later on, we will present a demo of how this prototype can address a configuration problem in cloud burst scenario. Finally, we will give you the conclusions of our works. As I said in the opening, the declarative approach perhaps is the most commonly used approach to solve the configuration problem. This approach has been implemented by some popular tools such as Puppet, CF Engine, Chef, and LCFG. The main feature of these tools is that they execute some actions to achieve the desired configuration from any state. This feature enables automatic correction for any drift from the desired configuration. Unfortunately, there is a critical shortcoming in these tools. That is, to reach the desired state of the system, they execute the actions in essentially indeterminate order. This fact could bring the system into a state which violates the system's constraint. Let me show you a simple example of this problem in the next slide. Assume we have a system that consists of two servers, A and B, and one client C. In the top left box, we have the current state of the system. That is, A is running, B is stopping, and C is using a service such as DNS service that is running in server A. Sysadmin would like to change the configuration in such a way to achieve the desired state in the top right box. That is, A is stopping, B is running, and C is using the same type of service in server B. But in implementing the changes, sysadmin must satisfy the constraint, which is C must always refer to a running server. So what happens if we use declarative tool to solve this problem? To solve the problem using the declarative tool, first we must declare the desired state as follows: A.running equal false, B.running equal true, C.service equal B. Then we submit this desired state into any declarative tool which will execute some actions to reach this state. Unfortunately, since the tool executes the actions in indeterminate order, then there are 6 possible sequences of states that can be reached by the system, while only one of them, that is number 6, is the right sequence, while other sequences violate the system's constraint. For example, in the first sequence, server A is stopping while C is still referring to server A. That is why we can see that the declarative tools are highly likely producing the wrong sequence. Actually, in real life, sysadmin can still satisfy the constraint by using the declarative tool, but he must perform the configuration changes in several steps, one by one. In the first step, he must make sure that server B is running. Then in second step, he sets C to refer B. And the last step is turning off server A. These manual steps are something that we would like to eliminate in our prototype. So how can our prototype solve the problem? The main key to solve it is that all actions must be orchestrated in a workflow. By executing the workflow, the system can achieve the desired state and still satisfy the given constraint. To orchestrate the workflow, we use a technique called as automated planning. This technique will generate a workflow from a given pair of initial and goal state. But the main recipe in this technique is the definition of action. Essentially, in the declarative approach, each action does not have precondition and effect. Precondition is the constraint that must be satisfied before a particular action can be executed, while effect is the condition after executing the action. In automated planning, all actions definitions must have precondition and effect. This information will be used by the planner to generate a workflow that can achieve the goal state while still satisfies the system's constraint. Mainly, our prototype requires four information, that is the desired state, the global constraint, the current state, and the actions. Sysadmin only requires to declare two information. First is the desired state of the system, and second is the global constraint that must be satisfied not only in the final state but also in the intermediate state during the implementation of configuration changes. In this case, the global constraint is c.service.running equal true. It means that C must always refer to a running server. On the other hand, the current state of the system is acquired automatically by a monitoring agent which runs on each managed node, while the actions are defined by the experts, system engineers, or software engineers. Currently, in our prototype, we use a planner called LPG to generate the workflow. It receives an input in PDDL language, a language which is widely used in planning domain community. So, to generate the workflow for implementing the configuration changes, we transform the information of desired state, global constraint, current state, and actions into a PDDL language and gives it as the input of the planner. Then, the planner will generate a workflow as its output. Since we use the control tier to coordinate the execution of the workflow, the prototype translates the planner's output into control tier's workflow. Each action of control tier's workflow is associated with a Puppet manifest, which is implemented by the Puppet on the managed servers to reach the desired state. Before we go to the demo, first let me describe a little bit about our experiment. We've done an experiment using the prototype in a cloudburst scenario. So what is cloudburst scenario? In the scenario, suppose our company have an application service which is running in our private cloud infrastructure. Unfortunately, our private cloud has limited computing power, which sometimes cannot handle a spike of demand. That's why we need to migrate our application from private to public cloud within the following constraints. First, there is no downtime of service. It means that all clients must be moved to a temporary service during migration time. and back to use the main service after the migration. Second, we need to reconfigure the firewall so the clients in the internal LAN can have a connection to the service. Third, we must do full migration. We cannot just duplicate the application due to some reasons, for example, a limitation of license. This is an example of Cloudburst problem. Assume we have two identical web services, that is A and B. A is the main web service, and B is the backup web service of A. Both web services are running on two virtual machines. A is on VMX and B is on VMY. Currently, both virtual machines are running in our private cloud, and client C is using web service A. Because our private cloud cannot handle the spike of demands, then the sysadmin must migrate web service A to public cloud without stopping the client to use the service. The right side shows the desired state of the system, that is, web service A is running on public cloud while web service B is still in private cloud and not running. The main question is, how can our prototype solve this problem? So, to know about it, let's go to the demo. In this demo web page, we have three parts. First, the left box contains the current state of the managed system. In the middle box, the sysadmin can declare the desired state as well as the global constraints. And in the right box will contains the workflow which will be generated by the prototype. Before I show you the demo for solving the Cloudburst problem, let me show you first how the prototype can solve a simple configuration problem. Assume we have a system that has the current state as declared in the left box. This declaration means that we have the following resources. A is a service, B is a service, C is client, X is a virtual machine, Y is a virtual machine, and we have a private cloud infrastructure. The current state of the system are virtual machine X is in our private cloud and X is running. Virtual machine Y is in our private cloud as well and Y is stopping. Service A is in virtual machine X, service B is in virtual machine Y. Right now, service A is running, service B is stopping, and client C is referring to service A. We would like to change the configuration of the system into the following desired state. Service A is stopping. Virtual machine X is stopping. Service B is running. And client C is referring to service B. The global constraint that must be satisfied during the changes is C.service.running equal true, which means C always refers to a running service. If we click the submit button, then this all information will be processed by the prototype to generate the workflow in the right box. You can see that this generated workflow satisfies the global constraint. If you see in stages 1 and 2, the service reference of C is changing to service B after B is started, and in stages 2 and 3, service A is stopped after C is not referring to A. Okay, right now let's go to more complicated problem, that is Cloudburst problem. In this problem, we have the following resources. X is a virtual machine, Y is a virtual machine, A is a service, B is a service, C is a client. Pub-cloud is a public cloud infrastructure. Brief-cloud is our private cloud infrastructure. and we have FW as the company's firewall. The current state of our system are virtual machine X is in our private cloud. X is running. Service A is in virtual machine X. A is running. Client C is referring to service A. We also have a virtual machine Y in our private cloud, but Y is stopping. And service B is in virtual machine Y, and B is stopping. We would like to change the configuration of our system into the following desired state. That is, virtual machine X is in the public cloud. Client C is still referring to service A. Service A is still running, and service A is using firewall FW so that the client can connect to the service from internal LAN. And port 8080 of the firewall is assigned to service A, while virtual machine Y is still in our private cloud, and Y is stopping. During the changes, the prototype must satisfy a global constraint, which is c.service.running equal true, which means client C always refers to a running service. If we submit this information to the prototype, then we will get the workflow in the right box. And you can see that this workflow satisfies the global constraint and achieve the desired state. If you see stages 4 until 7, virtual machine is migrated after client C is not referring to service A, but referring a backup service, which is service B. And if you see stages 9 and 10, client C is changed back to refer service A after A is started. Another problem for this scenario is that how can we migrate back service A from public cloud to our private cloud? Sysadmin only must do a very simple changes in the desired state. Let me show you how this can be done. In the left box is the current state of the system, which means that service A is in public cloud, and C is referring to service A. In the middle box, we have the previous desired state. Sysadmin only needs to change 3 statements, that is, virtual machine X is in our private cloud, service A is not using any firewall, and service A is not using any firewall port. If we submit this new desired state to the prototype, it will generate the workflow in the right box. You can see that this workflow migrates virtual machine X, which has service A, from public to our private cloud, and also still maintains the global constraints. Finally, as conclusions of this presentation, we have shown you that our prototype can automatically generate the workflow between any 2 states. To manage the system, the users only require to declare the desired state and the constraints, while the prototype will achieve this desired state as well as preserving the system constraints. This feature will enable autonomic reconfiguration, either to implement a new desired state or to correct any drift in the configuration. And the most important thing is that it can make the life of sysadmin easier than before. We would like to thank to HP Labs, which has given us a grant to support this research. Thank you.